This paper is titled Enhancing Practical Tractability of Lyapunov-Based Economic Model Predictive Control by Helen Durand and Dominic Messina at Wayne State University. The premise of this work is that the ability to verify that an automated system will operate a process safely is critical for the application of control to that process. A common control design used in the chemical process industries, where safety is of paramount importance, is Model Predictive Control, or MPC, which is an optimization-based control law with constraints including a process model. The objective function of the controller's optimization problem has traditionally been formulated to track a steady state, but a more general formulation of MPC, meaning one that uses a general objective function and is therefore known as Economic Model Predictive Control, or EMPC, because that objective function can explicitly represent process economics, may not track a steady state. Instead, it might operate a process within a region of state space. Then, safety is considered to mean that the state is maintained in that region of state space. An example of an LEMPC formulation with constraints that allow this safety concept to be guaranteed under certain control theoretic conditions is Lyapunov-Based EMPC, or LEMPC. This work explores the concept that perhaps verifying that certain theoretical conditions required for safety under this controller could be made easier, in the sense that an end user might expect the conditions required for safety to be more likely to be met for given parameter values used in the control law without explicitly checking, by using a modified implementation strategy. In this implementation strategy, state measurement use in assessing and reacting to safety considerations is decoupled from the sampling frequency of the LEMPC. State measurements are assumed to be available much more frequently than the frequency with which the LEMPC uses them, and are used to check throughout the LEMPC sampling period whether the closed-loop state has left a subset of a set referred to as the stability region, which is an estimate of the region of attraction. When the closed-loop state at any of the times that the measurement is taken is outside of the subset of the stability region, a backup controller begins to be used instead of the LEMPC for the remainder of the LEMPC sampling period. The result of this is that it allows less restrictive conditions to hold on the size of the subset of the stability region than if the LEMPC sampling period was used to design the subset of the stability region. This may increase confidence that closed-loop stability or safety would be maintained under the controller, even if the size of the subset of the stability region was not rigorously set using control theory, by effectively making a larger number of sets have the ability to guarantee closed-loop stability, such that even potentially ad hoc selection of a set may have a greater likelihood of maintaining the closed-loop state in the desired region. It also opens up the possibility of potentially tuning the size of the subset of the stability region online by modifying it to be smaller whenever the backup controller is implemented in the sampling period after a given size of the stability region subset is used. We gratefully acknowledge the National Science Foundation and Wayne State University for their financial support.